Okay, so the second lecture about chapter 1 will be about curve counting. Now, tropical algebra is really the max plus or min plus algebra in our case. And this algebraic structure has been invented and reinvented many times. So the term tropical is in the honor of a Brazilian mathematician who was French. His French colleagues used the adjective tropical. But historically, this was invented and reinvented outside the core mainstream of pure math, in optimization, control theory, often in the engineering literature. But it was only about maybe 15, less than 20 years ago that tropical geometry became an exciting area within core theoretical mathematics, and it's the work on curve counting, work of Mikhalkin in particular, that propelled these ideas to the forefront of geometers, algebraists, number theorists, topologists. So I'd like to tell you a little bit about this. So let's say C is a classical plane curve, a smooth curve of degree d in the projective plane. And this is here the complex projective plane. Now that's a Riemann surface. And the genus of this curve, or the genus of this Riemann surface by the degree genus formula, is a half times d minus 1 times d minus 2. d minus 1 choose 2. So this is 0 if d is 1 and 2, and then it goes on 1, 3, 6, and so on. Okay, now we're going to, for illustration today, we're going to use the case d equals 3, 4, in which case the genus is 3. So if you plug in d equals 4, a plane quartic curve is a genus 3 curve. It's a Riemann surface with 3 handles. So as a Riemann surface, maybe the picture looks like this. I'm not very good at drawing this. So 1, 2, 3 holes. So this is the picture of a genus 3 orientable surface, and that's the Riemann surface that you get by a plane quartic curve. Now if you draw the real picture, the real curve, this is the fixed point set of an involution on this curve called complex conjugation. Right? So complex conjugation gives an involution, and this leads to the real curve, and the real curve has at most 4 connected components, and typical interesting shape that you might see are these 4 bean-shaped curves. So this orange picture is the real part, typical real curve. So there's the complex picture in yellow, there's the real picture in orange, and then to the right of it, let's draw the tropical picture. So the tropical picture might look like this. So I'm drawing 3 honeycombs, 3 hexagons to indicate the genus 3. So here's a graph of genus 3, and then I attach some unbounded stuff to make it balanced, right? Tropical curves should always be balanced. So to make it balanced, here we now need 4 southwestern half rays, 4 eastern ones. There's my tropical curve, a genus 3 curve. So the complex picture and the tropical picture in green match as far as the genus goes. And in the real picture, well, the number of connected components by Harnack's inequality is the genus plus 1 at most. So real, complex, tropical. And now let me draw the dual picture to the green picture. So we argued that we get this by drawing the Newton diagram, Newton polygon, 1, 2, 3, 4, 1, 2, 3, 4. So I'm drawing the 15 terms in a general polynomial of degree 4 and 2 variables like this. And then this is the picture dual to a triangulation of the left picture. Now what I want you to notice is that the genus is the number of interior lattice points, right? corresponding to these cycles. So let's record. This is also the number of lattice points in the interior of the Newton polygon of the curve. I'm taking lattice points, so these are points in Z2, and I have to close one more parenthesis, right? So the genus is the number of interior lattice points in the polygon. Okay, now for general curves, we look at all the curves of degree d, then they themselves form a projective space, right? Quartic curves have 15 terms, and the 15 coefficients should be thought of as homogeneous coordinates on a projective space of dimension 14, right? So quartic curves themselves form a P14, so curves of degree d form a projective space Pn, where n is 1 less than the number of monomials. Now, the number of monomials is d plus 1 choose 2, but I'm going to write this in a funny way. I'm going to write this as g plus 3d minus 1. So I claim that the dimension of the space of curves of degree d is the general genus given up there plus 3d minus 1. So for a quick reality check, so let's plug in d equals 3. So then we get, 3, oops. I hope I'm doing this right. Oh yeah, let's try. So 3 plus 3, 3 times 3 is 9 plus 3. Okay, well, somebody will check, right? So I wanted this to be 14. Oh, 3 is 4, thank you. Yes, very good. It's a very hot day, tropical in Leipzig. So 3 plus 3 times 4 makes 15, minus 1 makes 14. Okay, so this is the dimension. Now as the curve becomes special, if I move my coefficients to special position, the curve might acquire singularities, and typically the genus drops by 1. If you have a singularity, so it drops by nu if C has nu general singular points called nodes. Okay, so for simplicity, let me say it like this. If I have a curve that in a general fashion acquires new singularities, each time there's a singularity, the curve drops 1 in their genus. So this curve counting refers to the determination of certain numbers that are called Gromow-Witten invariants. So these are the Gromow-Witten invariants of the projective plane. So these are numbers, capital N, that depend on the degree and the genus of a plane curve. So now I look at singular plane curves of a given degree d and a genus g. So the genus will be at most the expression up there, but if it's less than that, then the difference counts the number of singular points. So the Gromow-Witten number that we're interested in is the number of irreducible curves the number of plane irreducible curves of fixed genus, genus G, and a fixed degree D, like 3 and 4, for example, that pass through a certain number of given points, that pass through the right number, and the right number is G plus 3D minus 1 general points in the plane. Okay, so now you see this number reoccur. Here G is the general number, but here G is any number less or equal to the general number, right? So I might look at singular curves, and then whenever I require one more singularity, then I have one less degree of freedom that I can impose by requiring passage through a given number of points. So let's calculate a few of these numbers. So here are the first examples of such Gromow-Witten numbers. So n01 I claim, just like n02, is equal to 1. Okay, so let's look at this. So n01, so 1 is the degree. Right? So I'm looking at lines, straight lines in the plane, and they have genus 0. Right? So n01 is the number of straight lines in the plane passing through 2 points. 0 plus 3 minus 1 makes 2. So how many lines pass through 2 given points in the plane? And the answer is 1. Okay? The next one, n02, right? So now I'm looking at quadratic curves. They also have genus 0, typically. Now evaluate this again. So 0 plus 6 minus 1 makes 5. So how many quadratic curves pass through 5 given points in the plane? And the answer is 1. Well, that's because I have a linear constraints on the P5 of conics in the plane. Likewise, n13. Well, these are now cubic curves. A cubic curve without singularities has genus 1. Right? So this is a g equals 1, n equals 3. So we plug this in one more time. So we have 1 plus 9 minus 1 makes 9. So then the question is, how many cubic curves pass through 9 given points in the plane? Well, the answer is 1. Right? So this is very easy interpolation. Okay. Now let's get some more interesting numbers. So a little bit more interesting is n03. That's 12. Right? So this is cubic curves that have now one singular point. So now I'm not speaking about general cubic curves. I talk about special cubic curves that have one singular point. That drops the genus by 1. That makes them rational. And I claim the number of rational points passing through 8, the number of rational curves passing through 8 given points is 12. And you can see this nicely algebraically because this 12 is the degree of the discriminant that you can look at quite explicitly in example 172. Right? The discriminant of a plane cubic curve is a polynomial of degree 12 in the 10 coefficients of a plane cubic. It's a small polynomial. It has only 2040 terms, but it has degree 12. Right? So in this P9 of all plane cubics, I have this degree 12 hypersurface, and then forcing the cubic to lie on 8 points means I'm stabbing this hypersurface with a line, and it will stab the hypersurface in 12 points in its degree. Now let's move on to our quartic curves. So n 3, 4, well, this is the general case. In the general case, it's always 1, right? A general plane quartic passing through 14 points, there's only 1, right? But these numbers go up as we acquire singularities. So if we have one singular point, then it's a genus 2 curve, and there are 27 of them. Then there's n 1, 4, that's 225. So let's plug in one more time. So this is 1 plus 12 minus 1. So if you plot 12 given points in the plane, then I claim that this Gromow-Witten number 225 says that 225 elliptic curves with 2 singular points that pass through the 12 points. And then finally, the rational curves n04 is 620. Right? So this is the number of rational quartics passing through 11 given points in the plane. So the theorem, so this is classical geometry, and these numbers are not so difficult to compute using classical geometry, 19th century geometry of plane curves. So the theorem that brought in tropical geometry can maybe informally be stated like this. So this is 174. So these numbers, the Gromow-Witten invariants or the Gromow-Witten numbers, can be computed tropically. So you can, everything that's on the left blackboard, you can, and in fact we will, phrase tropically in the next 15, 20 minutes, and then doing a tropical count using combinatorial methods, you get exactly the same numbers. Let me embark on the relevant definitions that we need to make sense of the statement of this theorem. First of all, let me say a tropical curve. So you have a plane curve. A tropical curve is said to be smooth. Well, they're not smooth in the usual sense, right? Because I have the piecewise linear nodes and so on. So we need a combinatorial notion of being smooth. And the notion is, in the plane, if it is dual to a unimodular triangulation, to a so-called unimodular triangulation of the Newton polygon. Well, we already saw in the examples in the first lecture that a tropical curve is the dual graph to a subdivision of the Newton polygon. Generically, if the coefficients are sort of random and you pull these as heights out of the blackboard plane towards you, you will see a triangulation. And it's unimodular if all the triangles have the smallest possible volume, area, right? So a lattice triangle in the plane has a half integer area, and unimodular means I require every triangle to have area half. So the area is the base times height divided by 2. If that comes a half, then I call this, and this happens everywhere, I call this a unimodular triangulation. And the examples we saw in the first lecture were unimodular. I'm going to say the curve is simple. Well, if it's not quite smooth, but if I allow some singularities, so a simple curve, it looks locally. If it locally looks like this, at every node, either you see a trivalent node, dual to a triangle in the subdivision, but this could now be a big triangle, just any triangle, not necessarily unimodular. And you also allow some 4-valent nodes, but they're only allowed like this. You really have locally 2 segments intersecting in a straight fashion, right? So dually in the triangulation, this corresponds to a triangle, and this corresponds to a parallelogram. Right? So if you see in your subdivision only triangles and only parallelograms, then we're going to say it's a simple curve, and then these are the local features in the curve. Now we're going to define the genus of a simple curve. So if I have such a simple curve, so I locally look like this everywhere, I'm going to define the genus of such a curve to be the following quantity: a half t of c, I need to define this, minus a half r of c, I need to define this, plus 1. Okay, so t and r will be integers, and they are as follows. So t of c is the number of trivalent vertices. T for triangle, you count how many trivalent vertices you see, or equivalently how many triangles you see in the subdivision. And then R is for ray. R of C is the number of unbounded edges. Okay. It's a combinatorial exercise that this definition, this genus is a non-negative integer, right? So these could be half integers, but then they cancel. So there will be always an integer, and then that integer actually is non-negative. Okay? So So let's see if we have a general dense polynomial. So if C is a general polynomial of degree d, let's compute these numbers. So then T of C is d squared, right? Well, let's, for simplicity, assume that we have a unimodular triangulation. Let's say dense and generic and unimodular, right? So if I have plane curve of degree d, I see d squared nodes in the triangulation. And you know this from Bézout's theorem, right? By Bézout and by stable intersection, if you take the same curve of degree d twice, it has d squared intersection points. And these are the stable intersection points where the nodes of the curve, right? So general smooth curve of degree d has d squared nodes, and they will all be trivalent. The number of rays is equally easy. So R of C is equal to 3d, right? Because they're d northern rays, d eastern rays, and d southwestern rays for a total of 3d. Well, let's look at this number. So we take a half d squared minus a half 3d plus 1. We do a little bit of arithmetic, and we get the formula up there. So this formula, the number from the degree genus formula, is exactly d squared over 2 plus minus 3d over 2 plus 1. So this works out. I need one more definition. I'm going to say the contribution, so this will be the contribution to curve counting. So the contribution of a particular curve C in my count is the product of all the normalized triangle areas. And by the normalized area, I mean the usual area times 2. Right? So I'm going to normalize so that a smallest lattice triangle has area 1, and so on. So if you have a smooth curve, well, then all the triangle areas are 1, and this becomes 1 times 1 times 1 times 1. So a smooth curve contributes 1 to the count we're embarking on. But if the curve is singular, right, if I have these trivalent nodes that are not smooth points, or I have some of these parallelograms, then I might get a bigger number. I might have to multiply triangle areas that are bigger than 1, so somehow more singular, the bigger the contribution. So it is 1 for smooth tropical curves. So now let me state the theorem again in a more precise form. So this is theorem 175 in the book, and this is known as Mikhalkin's correspondence theorem, or correspondence principle, here in its most basic version for plane curves. And it says the following: the combinatorial number agrees with the geometric number. So the combinatorial number is the number of simple tropical curves of degree d, so having the right number of northern, eastern, and southwestern rays, and genus, given genus G, with the definition of genus over here. So I'm counting curves of a given degree in the given genus. Well, passing through the correct number of points. So this is G plus D, 3D minus 1 general points in the plane, counted by contribution. Right? So you plot these points in the plane. You only allow simple curves that have the given genus and degree and pass through these points. But then such a curve might have a contribution defined as this. It's a positive integer. You add them up. And then that sum equals the Gromow-Witten number, the classical Gromow-Witten number NGD. Okay? So it says that this object that we defined in terms of complex geometry of plane curves agrees with this combinatorial count with the definitions here on the right blackboard. Okay, let's see some calculations. So I'm going to compute now the number 620. So remember, 620 is the N04 Gromow-Witten invariant. So this is the number of rational quartic curves passing through 11 given points in the plane. Now, what I'm going to do is I'm going to digress a little bit. There's a nice recursion for these Gromow-Witten numbers in the genus 0 case. So I want to discuss this for a moment. This is for rational curves. So even the case of genus 0 is most interesting. And you saw in the examples, the genus 0 case always gave you the largest number. Right? So those are, in some sense, the interesting ones. And the formula that I'm going to give is due to Kontsevich and also due to 4 physicists, Witten, Dijkgraaf, Verlinde, and Verlinde. So this is also known as the WDVV formula. So the WDVV formula says the following. It's a recursive formula for N0D. So this is the number of rational curves of degree D passing through the right number of points. Okay? So this is a sum over pairs of integers, D1 and D2, that sum to D, and they're both positive. So I look at all possible ways of writing my degree as a sum of 2 unordered positive integers. Then I have a coefficient, and the coefficient is D1 squared times D2 squared times 3D minus 4, choose 3D minus 1 minus 2. One more term. D1 cubed times D cubed, D2 times another binomial coefficient, 3D minus 4, choose 3D minus 1, close the parenthesis. Well, that's a big number depending on D1 and D2. And this I multiply by N0 D1 times N0 D2. Okay? Now that's a recursion, right? Because the D1 and the D2 on the right side are smaller than the D I'm computing. Okay? Let's do an example. Let me do a calculation for you. So I claim that the number 620, which is this number when D is 4. So let's say now D is 4. Well, there are 3 terms. So there's one term for 1, 3. There's another term for 2, 2. And then there's 3, 1. Right? So if I take the integer 4 and I write it as a sum of 2 positive integers ordered, there are these 3 ways. Right? So I have to do this 3 times. The first one is 9 times 8, choose 1, minus 3, 8, choose 2. Now this I have to multiply with the Gromow-Witten number for rational curves of degree 1. Those are lines in the plane. And degree 3, so this is 1 times 12. So that's 12. Okay, so I already know the smaller number 12. For example, from the beautiful discriminant that you saw in the book, that's a tiny polynomial, homogeneous of degree 12, in the 10 coefficients of a plane cubic, having only 2040 terms. The second term is the coefficient 16, 8, choose 4, minus 16, 8, choose 5. And then I have to take n02 times n02, that's 1. Right? That was the number of plane quartics passing through 5 points. And then here I have the last one is 9, 8, choose 7, minus 27, 8, choose 8, which makes 1. The whole thing times 12 again. And then evaluating this yellow number makes 620. Okay? Now why is that nice? Well, this is actually the recipe for a tropical proof. So this was proved before by Kontsevich, but a remarkable paper due to Gottman and Maclagan. So Andreas Gottman and Hanna Maclagan in 2008, they gave a tropical proof. So they took the ingredients in this formula and turned the ingredients into pictures. Right? Each of these ingredients, this is a sum of positive numbers. You're counting certain kinds of tropical pictures, each tropical picture indicating a degeneration in complex geometry, and then assembling all these combinatorial pieces, they rederive this formula. So this sort of circle of ideas, Mikhalkin's contribution and others who followed it, as I said, propelled tropical geometry, the geometry of the min-plus algebra, to the forefront of core geometers, algebraists, and topologists. I like to advertise in this connection, so our book is not the only book on tropical geometry. There is a book in the making by Grisha Mikhalkin and Johannes Rau. You can find the manuscript online, where they take a slightly different perspective from our book. It's a more synthetic perspective, but it's inspired, by a theory that then ultimately leads to these kind of results. So, a book by Mikhalkin and Rau. There's another book in the making on Essentials of Tropical Combinatorics by Michael Josvik, also coming out very soon. So there's a number of other sources that you can and should study alongside reading our book. Now in the last 16 minutes, I like to move on to section 1.8. So this was 1.7, curve counting, and this is, curves in the plane of a given degree, of a given genus, passing through a given number of points. There are many variants of this. You can count these curves on other surfaces. You can try to count higher dimensional objects. So this is called Gromow-Witten theory, and this has been intimately tied in with sort of synthetic tropical geometry in the last couple years. 1.8 is called Compactifications. So this gives you a glimpse, a tropical island chapter 1 glimpse of a subject that's being developed in detail in chapter 6. So again, in the very end, we're going to come back to this, but I'll just give you the basic idea of compactifications. So suppose you're given a variety. So this is a classical variety, and we're in C star to the n. So I'm always disallowing 0 coordinates. And the reason is that tropicalization is sort of taking the logarithm, like talking the logarithm. You're not allowed to take the logarithm of 0, right? So I'm taking n vectors of non-zero complex numbers, and I take the 0 set in there of a bunch of polynomials. So then what we're going to be interested in, we're going to seek a compactification. X bar, but not just any old compactification. We like to have a nice compactification. Well, first of all, X is not compact because I ripped out those points where coordinates are 0. For example, if I have a plane quartic, I ripped out 6 points. That was made visible by the tentacles of the amoeba. Right? But in general, I'm ripping out some points. Rip out some curves, some surfaces. I want to put something back in so that I get a compact variety. And I like this compact variety to have good properties, okay, whatever that means. Let's do an example. Let me show you how compactification might work. So let's take a plane curve C1 plus C2 xy plus C3 x squared y plus C4 x cubed y plus C5 x cubed y squared, where the c's, the 5 coefficients, are random complex numbers. Okay, so let's think about these coefficients. They're somehow generic. Ci are general complex numbers. Let me draw the Newton polygon. So here is the constant term. Then we have y. We have xy, x squared y, x cubed y, and then up here we have x cubed y squared. So it's kind of a funny quadrilateral with one interior lattice point. Okay. And this example, x is a curve, but it's a non-compact curve because it's an c star squared, and it turns out that this is a smooth curve. And that's because the coefficients are generic, right? So if you take the partial derivatives with respect to x and the partial derivative with respect to y, you set them to 0 together with f, then you have 3 equations and 2 unknowns, and they have no solution x, y in the non-zero complex numbers. Now, how would you compactify this? Well, if you studied, and you should have studied, the last chapter in the undergraduate textbook by Coxell-O'Shea, then the natural way to compactify is take the projective closure. Right? So whenever you have a affine variety or very affine variety, then the closure of this curve in P2 is easy to compute. Right? This is simply, you introduce a homogenizing variable z, and then you homogenize this to a homogeneous polynomial of degree 5 in 3 variables x, y, z. And you can do this for arbitrary ideals according to the last chapter of the Coxell-O'Shea undergraduate book. So then this closure is simply that projective curve, and what that does, it adds 2 points, but these are singular. It adds 2 singular points. Right? You glue in 2 more points, but this projective curve is very singular at those 2 points. You can make a calculation, and these are very singular. Well, the other thing you can do is you could compactify, for example, not in P2, but in P1 times P1. Or algebraically, you could separately homogenize. Right? You can introduce a homogenizing variable x twiddle for the x and a y twiddle for the y. Right? Then you have a bihomogeneous polynomial in 4 variables, x and x twiddle, y and y twiddle, bihomogeneous of degree 3, 2. Right? That you can also do. Now that adds 3 new points. That throws in 3 new points. But one of them is still singular. Right? So you've created a compactification with 3 additional points. Two of these are good in the sense that the curve will now be smooth at those 2 points, but one of them is still singular. But the best thing to do is to use the so-called tropical compactification. In the tropical compactification, you don't do anything. You let the curve and its Newton polygon speak to itself. Just let the curve tell you how it wants to be compactified. And what the curve tells you, and if you listen carefully, then the tropical compactification adds 4 points, and it's smooth. Now those 4 points correspond to the orange edges of the Newton polygon, so it turns out that each edge will contribute a point, and so you have this 4 additional points, and this gives you the tropical compactification. So the geometry here is that x bar is an elliptic curve. So it's still true that the 1 interior lattice points indicates the genus of the curve. It is still a genus 1 curve, the kind of curves that cryptographers like for their group law. So this elliptic curve over the complex numbers is genus 1, so it's a torus, but minus 4 points, 1 for each of the orange edges of the Newton polygon. Right? So this is an example. Right? So if you did what the algebra tells you to do, if you did what the last chapter of Cox-O'Shea tells you to do, to homogenize naively with a new variable z, or possibly 2 new variables, x twiddle, y twiddle, you're a little bit off. But if you let the Newton polytope speak, you will do the right thing. Let me put this in context. Yes?
X bar and elliptic curve minus 4 points and stick of that.
No, x, I'm sorry, x without the bar, sorry, typo, yeah. So x, the open non-compact curve is a torus, a genus 1 Riemann surface with 4 points removed. And then, well, if we put those 4 points back in, it'll be smooth. So that's not surprising, but what the wrong thing is being done by the algebra. Right? So if you homogenize the equation, that would do the wrong thing. So let me end today with a little bit of philosophy on compactifications. So you do this in general. There's the general setting. So in general, we are in C star to the n, we have any variety, right? So I have a 5-dimensional variety in the 11-dimensional complex algebraic torus, and I want to find a good compactification. Well, one way to generalize plane curves is to look at curves in an ambient dimension n. So you keep the dimension of the object small at 1, but you increase the ambient dimension. Another way what you can do is you could look at hypersurfaces, right? You say, well, plane curves, in particular hypersurfaces, you keep the codimension small, right? You look at hypersurfaces, right? So here we're looking at curves in high dimensions. Here we look at codimension 1 in general. And another thing that we really like are linear spaces. Now what's happening when you discuss compactifications? Well, so for curves, I claim the geometry is easy. Right? I made it sound easy here, and it is easy. Right? A complex curve is a Riemann surface. You removed a bunch of points, and you just put them back in. Right? So this is sort of unsurprising from a geometric point of view, but the algebra is difficult. So So if you want to write down in a Grobnerian Coxeter-O'Shea fashion the algebra that mirrors this easy geometry, the algebra will be quite complicated. Okay? So for curves in high dimensions, easy geometry, challenging algebra. Now for hypersurfaces, the algebra is easy. If you have a hypersurface, really all you need to do is homogenize. Here you have to homogenize in the so-called Cox coordinates. But if you have a single equation, you want to calculate the tropical compactification, the algebra is quite simple, and the combinatorics of the Newton polytope is pretty easy. But the geometry and topology is not. So if I give you a polynomial of some degree and 5 variables, I look at the variety in C star to the 5, let's say it's smooth, and I ask you to describe the geometry of the compactification, that's more difficult. Now finally there's a situation of linear space. So what's interesting about linear spaces? Well, what can you say about linear space? Well, let's say, for example, we in C star to the 4. And suppose in this, here you have a variety given by 2 linear equations. Okay, you want to solve a system of 2 linear equations and 4 unknowns, but these unknowns represent non-zero complex numbers. Well, you get a plane with something removed, right? You get a plane with 5 lines removed. Right? You're removing the intersection of your plane with one of the coordinate hyperplanes makes a line. Right? So x1 equals 0 restricts to a line in that plane. Think about the plane as the blackboard plane, and then you're removing that line. There are 4 more because there are 3 other coordinates, and then there's a plane at infinity. Right? So the solution set to a system of 2 linear equations in 4 non-zero complex numbers is the complement of 5 lines in the plane. So our affine variety is the non-white part of the blackboard. That's our variety. But I cheated because my blackboard and my chalk is real. We really need a complex chalk and a complex blackboard, right? So really this picture is 5 Riemann spheres touching pairwise. Right? A line over the complex number is a Riemann sphere. Take 5 table tennis balls, 5 ping pong balls. Go in sufficiently high dimension, make those 5 ping pong balls touch pairwise, and the variety is the complement of those ping pong balls. It's a 2-dimensional complex surface or a real 4-dimensional variety. It has interesting topology computed by the Orlog-Solomon algebra, and that's the combinatorics of matroids. So the word matroid will come up a lot. So linear spaces and compactifying linear space in this sense, compactifying the complement of our 5 table tennis balls. That compactification is driven by the combinatorics. So let me summarize again. If we just start with curves, Riemann surfaces, well, the geometry is easy. We just stick in the points we removed. The algebra is tricky. To communicate this to your computer algebra system in a polynomial ideal fashion is quite delicate, even for curves. For hypersurfaces, it's the opposite. I argue the geometry is difficult and the algebra is easy, but then the linear case is particularly nice, and it becomes very, very combinatorial. But the bottom line is, many of your friends in algebraic geometry, they struggle. They struggle to find good compactifications. It's a subject. Finding, constructing, building good compactifications is a difficult subject. Sometimes you're very lucky. You don't need to do anything. Right? Tropical geometry is the art of letting a variety compactify itself. Right? So the tropical variety tells you its own compactification. Anyway, so this was to give you a glimpse. We will return to this topic and to tropical compactifications in the last chapter 6, in the last of the 12 lectures. So thanks for your attention. And maybe we can take questions from the audience or maybe online. Yeah, so I will not, give you the full theory, but so in this case, since we're over the complex numbers, the tropical curve more or less looks like the inner normal fan of, so the curve will be some balanced graph that looks like this. So these are 4 rays in the plane. That's a so-called one-dimensional polyhedral fan. This is a polyhedral fan that has 4 one-dimensional cones and 1 zero-dimensional cone. And this specifies something called a toric variety. So chapter 6 is called toric varieties, more or less. And then the closure of X in this toric variety is the tropical compactification. So the tropical variety is a picture like this. This picture indicates a classical toric variety, not complete, not compact, but X closed will be complete and will be compact. So this is something we'll learn in chapter 6. So let me repeat the question. Is the right compactification the one that's given by the Newton polytope? And the answer is yes. So that's the content of this word easy, right? So if I have a single hypersurface in general, I have a Newton polytope, and then that Newton polytope gives a toric variety, and I'm compactifying there. So in some sense, that's an old story, right? So there's an old story of toric geometry to speak about polytopes, Newton polytopes, and compactifications. And the term non-degenerate with respect to the Newton boundary is often found in those papers. So this is this special case of hypersurfaces and complete intersections. And I took the liberty of attaching the adjective easy here. This is the thing we want to get away with. So the person in the audience who asked the question, what we want to do in tropical geometry is to get away from that. So tropical geometry is the art of doing away with Newton polytopes. Right? We want to deal with arbitrary varieties that are not hypersurfaces. But in this special case, indeed, this tropical variety or this Newton polygon is what drives the compactification, 1 new point per edge. Okay, so the question is, what is the classical meaning to these simple curves? So these simple curves they may be singular, but not too badly singular. And so there's a notion of contribution. So in this correspondence theorem, what we're saying is if you have a simple curve of a given contribution, say 12, there will be 12 classical curves coming from this. And in some sense, you can construct those classical curves in this manner by, say, Maslov dequantization. Okay, so the question, is there a tropical generalization of Castelnuovo? So Castelnuovo I know for curves in higher dimensional spaces. So for example, if you have curves in 3-dimensional space of a given degree, then there's a range of what the genus can be. So if you tell me you're interested in space curves degree 6, the genus will be 0, 1, 2, 3, or 4. And I believe the answer is yes. There are tropical versions, but things are a little bit more tricky already for curves in 3 space. So in 3 space, there are balanced graphs that look like a tropical curve, but they're in fact not. So I think there's a version of Castelnuovo, but we have to be very careful because there are in 3 space already curves that look like they are tropicalizations of classical curves, but in fact they're not. So the question is the 12? So I can think about these Gromow-Witten numbers. They count the number of solutions to certain very special systems of polynomial equations. So what the correspondence theorem says that in this context, solving the equations tropically gives the same number as solving them classically. The question is then actual correspondence, and the answer is yes. So the charm of tropical geometry, it provides you numerical algorithm. It, in most cases, produces so-called numerical homotopy methods. So these are numerical methods in algebraic geometry for producing the classical complex solution from the degenerate picture. So there is always, so in the background to this, there is always a degenerate case, and you'd like to have a way of homotoping to the classical solutions, and in principle, these kind of results furnish this. Realizing it in practice and implementing it in practice is a different story. Okay, well, if there are no further questions, I thank everybody for coming, both here in Leipzig and online.